So welcome everyone to lecture 6 of your favorite introduction to quantum optics. So let me remind you a bit of what we have done so far, or what we did last week. Actually, last week we finished this long chapter on the quantization of the electromagnetic field and the states of the harmonic oscillator and so on. And then we started the new chapter on the quantum theory of matter. But in particular, we started focusing on atomic systems and the hydrogen atom. So let me just go through that very quickly again. So just reminding you what we did. So what we saw in the previous chapter is that the electromagnetic field, it's made out of degrees of freedom that behave as harmonic oscillators. And this means that the degrees of freedom have a uniform spectrum, okay? A uniform energy spectrum. Now, with full generality in quantum optics, we refer to matter as any system that couples to the electromagnetic field and that has degrees of freedom that are described by a non-uniform energy spectrum, okay? So for example, this one in here, where you see that each transition between energy levels is completely different from the other. Now, this might seem to complicate things because the spectrum now is very complicated and in general it has no structure. But actually what we discussed and we will see in detail today is that because each transition has its own spectral fingerprint, so it has its own energy, its own frequency, then each transition is unique. And this allows us to focus on just specific transitions that we care about and forget about any other transition. So at the end, the spectrum becomes very simple in practical terms because you focus only on a couple of transitions or whatever you're interested in. So what I told you is that in order to fix ideas, we would go first through a bit of atomic physics and a bit of how is the spectrum, the energy spectrum of atoms, and in particular the type of atoms that we use the most in quantum optics. And we started with the simplest atom, which is the hydrogen atom. So the hydrogen atom, it's very simple. You have studied it in quantum mechanics. So then this is hopefully just a reminder. So it is composed of one proton that is very massive compared to an electron. Okay. Then the proton has some spin degree of freedom, the electron has some spin degree of freedom, and then the other degree of freedom that we care about is the distance in between them, okay, the separation between them. And the center of mass motion, we don't care about it at the moment. So it's just like a free atom or whatever. We will see what happens with it later in the course. We can use it for things. Then we discussed that the Hilbert space of this system, it's essentially a tensor product of the spin Hilbert spaces, which are two-dimensional for a spin 1/2 particle. And then we have the one associated to the three-dimensional motion of the relative coordinate. And this Hilbert space is just 3 times or three-dimensional version of the infinite dimensional Hilbert space that we used to describe the single harmonic oscillator. So you already know about it pretty well. Okay, so then within the simplest approximation, the Hamiltonian of this system is given by what we call the Bohr approximation form, which has a kinetic term, so just the kinetic energy associated to the relative momentum, and then a Coulomb interaction, so the repulsion, the Coulomb repulsion between the proton and the electron. So now what's important in here is that, well, we have a three-dimensional Hilbert space and 2 spin spaces, so we need 5 quantum numbers in order to characterize the eigenstates or uniquely characterized eigenstates of your space or a basis of your Hilbert space. And in this case, it's very simple to find 5 operators that commute and whose eigenvalues and eigenvectors we know very well. And in particular, what we discussed is that the orbital angular momentum, okay, so R cross P, orbital angular momentum commutes with the Hamiltonian. So the components of the orbital angular momentum, all of them commute with the Hamiltonian. The square of the orbital angular momentum also commutes, and the components commute with the square, okay? And of course, the spin operators commute with the Hamiltonian because the Hamiltonian doesn't depend on spin, and commute with the orbital angular momentum, which is an operator that acts on a different Hilbert space, okay? Then we have already 5 operators that commute, and this allows us to label the eigenstates of the Hamiltonian, okay, or a basis of the Hilbert space, by 5 quantum numbers that we collect in a single vector, n, and all of them have the following significance. So the Hamiltonian acting on the eigenstate n provides you an energy, okay, En. And what we saw is that for this particular form of the Hamiltonian, okay, this Bohr approximation, this Coulomb potential, the energy depends only on a single quantum number, n, and it's given by this kind of formula, is 0 divided n squared with a negative sign. I think I forgot to mention that you also have a part in the spectrum of this Hamiltonian, that it's a continuous part. So here we are talking only about bound states, which are negative energy states, and this form a discrete set. But you also have positive energies available, and this corresponds just to scattering states between a proton and an electron that do not get bound into an atom, but they can scatter and move away. And therefore, for large distances, these states are basically plane waves, okay? Or eigenstates of the momentum, of the relative momentum. But we don't care about these states. These are not atomic, proper atomic states. These are scattering states. So we care about these bound states with negative energy, okay? Then on the other hand, the next quantum numbers refer all of them to angular momentum of some sort. In particular, L is the quantum number associated to L squares, so to the square of the orbital angular momentum. And that can go only from 0 to n minus 1 for a given energy level n. On the other hand, the third component, so we have to choose one component of the angular momentum that we choose for the quantization, and we usually choose the third component, okay? This is what it's usually called in quantum optics the quantization axis, and what we show, so what we choose, is that we choose as quantization axis the third axis, so the set axis. You will see later that actually, in general, this quantization axis is chosen by, experimentally, let's say, by external fields. So if you put an external magnetic field, the direction of the magnetic field actually sets what is the quantization axis of your experiment, and to that axis we call set, okay? We will see it later. Then, as I said, we have the third component of the orbital angular momentum, which has a quantum number that we call magnetic quantum number, and it can go from minus L to L in steps of 1. And then we have the third components of the spins, which can have eigenvalues plus or minus 1, okay? Something I think I didn't mention is I didn't talk about the degeneracy of this system, the energy degeneracy. And you see that because the energy depends only on a single quantum number n, then you have degeneracy in all the other quantum numbers. So it's very interesting to note the following, that actually the degeneracy in the quantum number ml, or the third component of the orbital angular momentum, this is something that probably you have studied when studying rotationally invariant potentials, and rotationally invariant potentials, so potentials or Hamiltonians which are invariant under rotations, all of them have this degeneracy in the magnetic quantum number. So we call it essential degeneracy. So this is something that works for any potential that is rotationally invariant. On the other hand, There is also degeneracy in the orbital angular momentum quantum number, but this degeneracy, we call it accidental, because this is only because of the form of the Coulomb potential, the 1 over r, okay? Potentials that are not 1 over r are not degenerate in L. So the energy has to be labeled with two indices, N and L, okay? So I hope that you have seen these kind of things. But, and of course, we have the spin degeneracy because the Hamiltonian is independent of the spin. So overall, we have a degeneracy, which is 2 times 2 for the spins, so 4 times n squared, okay? So each energy has a degeneracy that it's quite massive or can be quite massive for large n. So what we are going to see now is that actually this is within the Bohr approximation, but once we start including better and better approximations to the Hamiltonian, all these degeneracies are completely lifted, okay? And so let's go now to it. And in particular, let me start just by showing you the following. So what I will be doing in this slide is I will be building the spectrum of the Hamiltonian, okay? And I will be doing more and more spectra depending on the Hamiltonian that we are studying to the approximation of the Hamiltonian that we are studying. So for example, in the Bohr approximation, we have seen that the eigenenergies depend only on a single index n, such that we have the possibility of having energies with n equal 1, n equal 2, n equal 3, and each of these energies have a degeneracy 4, 4 times 4, 4 times 9, and so on. So what I will show you now is with better approximations and more complicated atoms, all these degeneracies will be lifted, okay? So then let's start with the simplest thing that I want to start discussing, which is the following. So I have talked about the hydrogen atom, which is the simplest atom, but what happens with multi-electronic atoms? So multi-electronic atoms. So in general, you can imagine that the spectrum of a completely general atom with many electrons and so on can be super complicated. But luckily in quantum optics, we usually work with atoms that are relatively simple in the following sense. So we usually work with these atoms that are called alkali atoms, okay? Which are atoms that have a single valence electron. Okay, what does this mean? This means that you have a nuclei that can be formed by many protons, then you have many electrons, but all the electrons are in a closed shell, so they are, let's say, inactive. We are not going to touch them. They are very happily sitting in that closed shell. I will show you now an example. And then you have a single electron that is out of this closed shell. So it's in what we call the valence orbit. And then this is the only active electron that we are going to actually push around and move around and so on. So then it's similar to the hydrogen atom, except that the core of the atom is much more complicated because it's a positive nucleus and then many electrons surrounding it. So I show you what I mean exactly. So let me see if I can draw it properly. So what I'm saying is that we have, for example, a core with charge +3. So we have 3 protons and a number of neutrons. And then around it, we have, for example, 2 electrons, which are already very happy in a closed shell. Okay. And we have also 1 more electron that is outside the shell. And therefore, what happens is that this electron, what it sees, is no longer just a nucleus of 1 proton or even a nucleus of 3 protons. It sees all this structure okay, as, so let's say this positive cloud is what it feels as the core of the nucleus. So we still have the degree of freedom of the relative distance between this electron and the center of the positive cloud, okay? But now this positive cloud is much more complicated. But still we can make a very simple theory. In particular, this massive kind of positive cloud interacting with the electron, it still can be described as something similar to a hydrogen atom. Okay, so it's same as hydrogen, but with a slightly different potential. So the potential is still rotationally symmetric, we will assume, and we can approximate it in the following way. So we can still assume that it's so for a given position, it has somehow a Coulomb form, okay? But now, this positive cloud will have a charge that depends on the position, okay? So this thing in here is some type of effective, oops, let me change the color. So this setting here is some kind of effective atomic, so not atomic, sorry, but effective charge. So some kind of effective charge of this positive cloud. And in particular, when the electron is very far away, okay, of course, what it sees is just some kind of structure in the center that it's basically like one single nuclei that has a charge +1, because you have 3 protons and 2 electrons, so the overall charge is just 1. However, as it gets closer and closer and closer and it enters, let's say, into the region where it already sees the electrons, and then even closer, and it feels completely all the charge of the nucleus, then this charge moves up to 3, okay? So you have a position-dependent charge, okay, that goes from 1 at large distances to the full charge of the nucleus at short distances. So this means that this potential is no longer a Coulomb potential, it has a correction, okay? It has a correction that depends on space, and therefore, as we have seen, this automatically implies that for this type of atoms, the accidental degeneracy is lifted. Okay, and in particular, this means that now the Hamiltonian acting on your eigenstates will give you an eigenvalue that depends both on n and L. Okay, so this is a relatively simple situation still, or within this approximation, but we have lifted already one degeneracy by adding more atoms, more electrons. So the other thing that it's important here, it's about the spin of the nucleus, okay? The spin of this object here, of this nucleus here. So now the point is that before we had a proton, and the proton has spin 1/2, and that's how it is, and that's life, and we have to work with that. However, now we will have atoms that have many protons and many neutrons. So this means that the spin of the nucleus will be any number allowed by the composition of angular momenta of the fundamental spins that form this nucleus. And in particular, what I am saying is now that the eigenvalues of this spin operator, the nuclear spin, I square, these eigenvalues that I will call I, so I plus 1 h bar square. They can be anything allowed by the rules of composition of angular momentum. And in particular, for example, in this case, imagine that you have 3 protons and 3 neutrons. This means that you have 6 particles within the nucleus of spin 1/2, and therefore the angular momentum will go from 0 up to 6. So you can work with atoms of this type, okay, that have all these possibilities for the nuclear spin. However, it's also important to mention that it's not easy to change the spin, the nuclear spin of an atom, okay? You need nuclear processes. And we are going to do quantum optics experiments, which are relatively low energy. And this means that actually, once you have selected one atom or one species of atoms that have one particular spin, nuclear spin, then that will remain fixed. That will remain fixed throughout the whole experiment and so on, because you are not going to do any process that will change the total spin of your nucleus, okay? So then we don't have to add this quantum number to our label for the states, because we just assume that this quantum number I is something that is given. But you just need to understand that it doesn't need to be 1/2. It could be any number allowed by composition of angular momentum. Okay, so these are the most difficult type of atoms that we are going to study, these multi-electronic atoms with a single electron in an active shell, in an active orbit. But everything that we are going to say here, it's kind of representative of what happens for most atoms. So in particular, let me now represent the spectrum, the energy spectrum that we get from this new situation. So let me do it here. So now we have here an energy that depends not only on n, but also on L, okay? And so this will be for multi-electronic atoms. And then what we have seen is that what happens is that, for example, in the example that we have treated, what happens first to the n = 1 level? The n = 1 level has orbital angular momentum only equal to 0, which means that you can only have 2 spin states for them. So for the states in that energy level, and in particular, those ones correspond to the 2 electrons that are already, so let me maybe represent it this way. So the 2 electrons which are happily in their closed shell, okay? So those levels are occupied from now on. Now, what happens to the next level, to the n = 2 level? So now for n = 2, you can have 2 orbital angular momenta, L = 0 or L = 1. And what happens is that for this situation, so maybe I make it a bit bigger. So for this situation, we get a splitting of the 2 possibilities for the angular momentum, for the orbital angular momentum. And the same happens now for the n = 3 level. We get the possibility of having L = 0, L = 1, and even L = 2, which I will not represent. Okay? So you have seen that this lifts this degeneracy, and it's also interesting that I tell you something about notation. So you might see many times something that is called spectroscopic notation. that we will not use very much, but you might see it in books, and if you work in quantum optics and atomic physics, you will see it all the time, in which the way that we represent or we denote energy levels is by saying N, L, okay, but L is not a number, but we use a letter for each L. So for example, you have seen probably already in your quantum mechanics class that L equals 0, we call it LS, sorry. So this means that we say, when we say level 2S, we means N equal 2, L equals 0. Now the L equal 1, we call it P, and therefore we call this energy level 2P, so N equal 2 and P means L equal 1. And we can do the same for all the rest. So this one here would be 3S, this one here would be P, so 3P, this one here would be 3D, okay? And this is the type of spectroscopic notation that I'm pretty sure that you have seen already somewhere. Okay, so then you see that adding more electrons already makes the spectrum more complicated and it lifts some degeneracies. But we have even more lifting of degeneracies, and in particular, because the Hamiltonian that we have written, the Coulomb, so the Coulomb potential only, so this Bohr approximation is not exact, it's not an exact Hamiltonian, but you have corrections. And in particular, you have corrections for, you have two types of corrections. One are called fine corrections, and another type are called hyperfine corrections that probably you have heard about as well. So in particular, let me first focus on the fine corrections, so what we call the fine structure of the spectrum. And these corrections correspond to corrections of relativistic nature. So these are corrections that occur because actually, even though the electron is not moving at the speed of light, it's moving fast enough, or it has enough energy to bring in some relativistic effects. And of course, these relativistic effects mean that the kinetic energy will no longer be p squared, but it will be receiving a correction of order p to the 4, for example. But here I want to discuss another one, which is the so-called spin-orbit coupling. So some relativistic effect means or provides a correction to the Hamiltonian that is of the following type. Is of the type that the spin degree of freedom of the electron couples in this form with the orbital angular momentum L, okay? And it's very easy to understand how this correction changes everything, because we can always write this product SL, we can always write it as the total angular momentum of the electron. I will tell you in a second what it is exactly. So the square of that minus the spin square minus the orbital angular momentum square. And here, the total electronic angular momentum is just the sum, as you can imagine, of the spin and the orbital angular momentum. So this is something that we call, or usually we call, electronic angular momentum, okay? Now, the only thing that you need in order to find the new good quantum numbers, because now the quantum numbers associated to S and L will no longer be good quantum numbers because of this argument here, because now you can write SL as J squared minus S squared minus L squared, And the most important thing is that all these three operators commute. Okay? Then this automatically means that you can use the quantum number associated to the total electronic angular momentum. You can use it as a good quantum number, and you still keep the good quantum numbers of S squared and L squared, okay? So this automatically means that now the states in this Hilbert space, or the basis states in this Hilbert space, will be denoted by, again, 5 quantum numbers, but we will no longer have MS and ML, but J and MJ. And of course, for the nuclear spin, we didn't change anything. So now the good quantum numbers are these ones here. And let me just remind you that this will mean that the Hamiltonian acting on this good quantum, so this stays with good quantum numbers, will give you an energy, but now the energy will depend on 3 quantum numbers, not only 2, because you see that J appears explicitly in this spin orbit coupling, J squared, okay? So now the energy will depend also on the quantum number J, which is actually the quantum number associated to the square of the total electronic angular momentum. And which values can it take? So the ones allowed by the composition rules of orbital angular momentum, which in this case are L plus minus 1/2. Okay? Because the spin of the electron is 1/2. On the other hand, we can choose the quantum number associated to the third component of the total electronic angular momentum as the last quantum number that we use. And this is just given by MJ H bar. And in particular, MJ will take values from minus J in steps of 1 until plus J. Okay? So then now that we have another correction to the spectrum of the atom, so in particular you see it here that now the degeneracy in the magnetic quantum numbers of the electron is lifted, and now we get an index J, so which is a total electronic angular momentum. Let's see what this means for this representation of the spectrum that we were doing. So let me do it here. So I am going to now write the spectrum corresponding to the fine corrections. And the important thing here is that now the energy depends on N, on L like before, but also on a new quantum number J. And again, coming back to spectroscopic notation, usually in spectroscopic notation that we have here, we include this extra quantum number that we need for fine corrections in this way. Okay, so N, L sub J. So then again, we have here the 2 electrons which are untouched because they are in a closed shell. And now I have to show you how is the spectrum for the rest of the levels. So of course, now what we have is that the angular momentum 0, okay? How many possibilities do you have for the quantum number J? Remember that the quantum number J is L plus or minus 1/2, but 0 plus or minus 1/2, it's equal to 1/2 in absolute value. So this means that the L equals 0 levels are actually not touched, or if you want, they are not lifted. Any degeneracy of them is not lifted. Then on the other hand, so, and let me say that this would correspond to the level 2s and then we add here the j. The j is equal to 1/2. So it cannot be anything else. Now, for the other level, for the level 2p, now we will have a splitting of two possibilities. So we will have the 2p level with a total electronic angular momentum 1 minus 1/2, which is 1/2, or 1 plus 1/2, which is 3/2. Okay? And of course, the same happens for the levels at n equal 3. So we have the 3 is 1/2 because L is equal 0. And then in here, we have the two possibilities that I will not write explicitly of 3p 3/2 and 3p 1/2. Okay? So you see how it gets more and more complicated and more degeneracies are lifted, but still everything has a very nice structure that allows us to discuss in detail everything. So, so you see that now we only have degeneracy in two quantum numbers, okay? In particular, the quantum numbers that we are using at this level of approximation of fine structure are mj and mi. However, these degeneracies are also lifted once we consider the next corrections in the hierarchy of corrections, which are called or are known as hyperfine corrections. So, or in particular, so hyperfine structure, which refer to or typically refer to interactions between the nuclear spin and the electron. So the nuclear spin and the electron, which go beyond what we have written for with just the Coulomb interaction. Okay, and in particular, I want to discuss the simplest of these ones, which is just the dipole-dipole interaction, so the magnetic interaction, if you want to call it like that, between the angular momentum of the electron and the angular momentum of the nucleus. So this would be just a product of this type, okay? So the total electronic angular momentum couples to the spin, the nuclear spin. And again, following the same trick as before, this can be written as the total, I will define it in a second, but this is the total angular momentum of the atom squared minus the nuclear spin squared minus the electronic angular momentum squared. And this F is just the total angular momentum of the atom, which is just J plus I. Okay, so we call this atomic angular momentum. And again, the trick is similar to what we did before, because F square, I square, and J square, they all commute, which means that we can use the quantum numbers of F square as labels for the energy eigenstates and keep the quantum numbers of I square and J square, okay? So this means that now the basis states will be labeled with 5 quantum numbers, which are m, l. We keep the one of J square, but now we have to replace the other two by the one of F square and the third component of F. Okay, and this again we will call n, and this automatically means that the energy, so the energy eigenstates or eigenvalues now need to be labeled with 4 quantum numbers, n, l, j, and f, okay? And we have that F is the quantum number associated to the total atomic angular momentum. So this will be F plus 1 h bar square. And the values that this F can take are running from the J minus I in steps of 1 all the way to J plus I. Okay, and I remind you that I is just the spin of the nucleus, which is fixed for us. It's not something that we can change in the experiment. Okay, and then, of course, MF is the quantum number associated to the third component. Oops. The third component of the atomic angular momentum, which runs from minus F to F in steps of 1 again. Okay, so now what's important, or most important, is that we still have good quantum numbers, but now the energy depends on 4 of those quantum numbers, not only on 3. And again, we can go back to our pretty picture for the spectra. And what we see, sorry, let me keep the color code. And what we see is that these hyperfine corrections, which again leave untouched the core electrons, and now we will have the following situation. So now the energies depend not only on N, L, and J, but also on some F. F is a composition of angular momenta, so we need to choose as an example some nuclear spin. And just to make it simple, let me take as an example a nuclear spin equal 1/2. Okay, so just like if it was a proton, so just spin 1/2. Then for a given L, okay, we will have 2 possibilities for F. Sorry, for a given J, okay, J, we will have 2 possibilities for F. J plus 1/2 and J minus 1/2, okay? So then this automatically means that in this case, we have the following lifting. So let's say that this one that has J equals 1/2, we will have 2 possibilities for the energies corresponding to the levels F equal 1 and F equals 0. So 1/2 plus 1/2 and 1/2 minus 1/2. Now, for this one in here, we will have something similar because J is still, so this is a P level, so it's an L equal 1 level, but J is equal to 1/2. So F will still be equal to either 0 or 1, okay? Now, this one is a bit more interesting because in here you will get F equal 3/2 plus 1/2, that's 2, and 3/2 minus 1/2, that's 1, and so on, okay? So then you see that taking into account all the possible interactions that you have in your real Hamiltonian, then we have managed to lift all these degeneracies in 4 quantum numbers, okay? So this is as far as it gets without breaking rotational invariance in some way. So in particular, the magnetic quantum number associated to the total angular momentum of the atom, so MF, that's untouched, or that degeneracy remains unless you break rotational invariance in some way. And in particular, in quantum optics, it's very natural to break rotational invariance by adding an external magnetic field. So an external magnetic field, you have studied the Siemens effect, and this means that if you have a magnetic dipole sitting on a magnetic field, you can describe that situation with a Hamiltonian in which you couple the dipole to the magnetic field, and in particular, you get a Hamiltonian that will be proportional to the magnetic field itself, and then the component of the dipole, or the component of the angular momentum in our case, that goes in the direction of the magnetic field, which is what we call direction 3. That's what we define as the quantization axis. So this is what is called as the Siemens effect. Okay, and what happens now is that you see that because now the Hamiltonian depends on F3, okay, and I remind you that F3 has eigenvalue MF, okay, then now the energy will depend on that value, and in particular, you can start splitting all the possibilities in here. So for example, here we have MF equal 2, MF equal, so let me make more because we need 5. MF equal 1, MF equal 0, MF equal -1, MF equal -2. And all these 5 levels will have a different energy in general, okay? And the same with the rest, right? So I don't need to write them. So this is actually very interesting, because what I am telling you is essentially that even though in atomic physics or in the atoms that we use in quantum optics, it might look as if the Hamiltonian has a lot of degeneracy, so it has energy levels with a lot of degeneracy. Actually, if you zoom in, if you start zooming into them, you will start seeing splittings, and these splittings are large enough such that you can resolve them in the lab, and you can actually use the energy eigenstates that have no degeneracies at all, okay? So I hope that this is clear. This is essentially everything I wanted to tell you regarding atomic physics. I hope that many of these things are kind of review of things that you have seen. But if they are not, well, in the notes, I wrote this very carefully, so go to it and read it again. But in any case, this is not an atomic physics lecture, so I don't need you to know this by heart, and you are not going to make atomic physics calculations, okay? But I want you to know this because if you work in quantum optics, you will be exposed to atomic physics all the time, and this is the absolute minimum that you need to be able to understand when people talk, okay, about quantum optics experiments. So now when you go to papers and they are using atoms, which happens all the time, you can understand when they start talking about hyperfine levels and so on and so forth, okay? So then before I proceed, let me make a final remark that we will need about atomic eigenstates, which is the following. It refers to the parity, okay? The parity of the atomic eigenstates. And when I say parity, I mean the following. So we can define a parity operator, which I will call pi, which is a unitary operator related to a symmetry that we call parity, that exchanges or transforms r, so the coordinates, into minus the coordinates. Okay, so we call this the parity unitary operator. Okay? Now, the first interesting thing to note about this operator is that because it has such a simple action, so it just exchanges the sign of the coordinates, then this automatically means that if I apply it twice, I just get the identity. So let me write the identity in this way. Maybe just so we don't confuse it with the I that I wrote before for the nuclear spin. So we are not going to talk about nuclear spin anymore. Be sure of that. But I write just as 1 with a hat. So as I said, if I apply it twice, then I do nothing. This automatically means that the inverse of the operator is equal to, of course, the dagger because it's unitary, but it's equal to the operator itself. And then this automatically means that the eigenvalues of this operator that we will call pi are plus or minus 1. Okay? So probably you are also familiar with discrete symmetries, and in particular with the parity operation. Maybe you studied it in quantum mechanics already, but this is pretty simple. Now, something interesting to note is that it can be proven, okay? And you have the proof in the notes. I don't want to do it here. It's not very difficult, just from the commutation relations, that the parity transformation on the momentum, okay, also changes the sign of the momentum. And this is something that you can prove from the previous expression. It's not something that that it's defined or anything like that. This automatically means that the angular momenta, okay, of your system remain untouched when you transform them. Okay, and we can continue with more observables and so on, because of course the orbital angular momentum is Rp. Then if you change the sign of R and P at the same time, then L doesn't change. Okay, so then let's see the following property. I think it's also pretty obvious that if your Hamiltonian is rotationally invariant, okay, then, so let's say if your Hamiltonian has spherical symmetry, as we have seen, at least for the simple atoms that we have studied, then this automatically means that the parity will not do anything to it because R changes to minus R, the kinetic term is P squared, you know, the spin and the orbital angular momentum do not change under the transformation. So then this automatically means that the Hamiltonian commutes with the parity operator. And this is very interesting because even though we don't need more quantum numbers, I mean, we already have 5 quantum numbers that define very well our spectra and so on, but it's still very useful to choose the eigenstates that we are working with, the basis states, as eigenstates of the parity operator, which we can do because the parity commutes with the Hamiltonian, okay? And this in particular means, as I said, that the atomic eigenstates N can be chosen with well-defined parity. And let me call pi n to the parity of the state n, okay? Then why is this interesting? Because then what happens, and this will be super important when we study the interaction between light and matter, so this is a fundamental result, a very basic result of quantum optics, and that is used all the time, is that if we consider the matrix element n prime of the relative coordinate, okay, so the relative coordinate is an operator. We can evaluate the matrix elements of this operator in the basis that we are working with, so the atomic eigenstates we have just defined. Then what we can do in here is, you see that if we insert here a parity square in these positions, what we will get is parity acting on R, okay, changes the sign. So it will give us a minus R. And then parity acting on the eigenstates n and n prime, because we have chosen them with well-defined parity, they just give you some eigenvalues of the parity pi n and pi n prime. But the matrix element stays the same. So the only thing that, so what you see is essentially that Rn, so Rn n prime, it's equal to the same matrix element and a sign, okay? So this automatically means that if the parity of n and n prime is the same, therefore this sign in here overall is a minus, okay, because you will have plus plus that gives you plus, or minus minus that gives you plus, and then a total minus. Then this matrix element will be equal to 0, because we have something equal to minus something. So if the parity of the two eigenstates is the same, they cannot be connected, okay, by the relative coordinate operator. So R cannot connect states with a same parity. So this is a very, very important result, and you will understand why in the next chapter when we study the light-matter interaction, because the transitions between energy eigenstates, you will see that when they are caused by light, they are proportional to these matrix elements, okay? And therefore, you see that you cannot generate transitions, at least you cannot generate with light, you cannot generate transitions between states when they have opposite parity, same parity. And so something interesting that this also means is that the diagonal elements of R are equal to 0, okay? Because of course, n has the same parity as n, okay? So this is something that we will use, and it's very interesting to take into consideration. Okay, so I hope that this is clear. As I said, we will use it much more in the next chapter, but it's good that we see it already here. So any questions until here? Because now we will move on to the next section of the chapter. So this is all the basic atomic physics that I want you to know. So if there are no questions, or otherwise just feel free to stop me anytime. Then what we are going to study now is something that is very, very important in quantum optics, which is called the two-level approximation, okay, of the description of the atom. And let me try to give you first an intuition of what is this two-level approximation, why do we do it, and what does it mean, and why is it a good approximation. And as we move along in the chapter, you will see how this approximation actually comes very naturally from the mathematics that we will develop and so on. So let me start just by saying first that perhaps by now you are a bit discouraged in the sense that light-matter interaction looks like a very complicated problem. So just imagine, right? Like, as we have seen, we have matter, and what is matter? So matter is something that has energy eigenstates that are not following any particularly simple rule, so a highly non-uniform spectrum. So this is matter. And then we have light. Light is something that can that we can shine on the system, on the matter, and it will have many frequency components, so photons of different types with different energies. But even to make it simpler, just imagine that you are shining a very monochromatic beam of light, which means that the photons have a very well-defined energy h bar omega, okay? So the frequency of light is omega. But even so, this looks like a very complicated problem because we have a highly non-uniform energy structure, and then you are shining light, and then you are giving energy to this structure, and then everything will start jumping around and so on, and it will be very complicated. So perhaps that's what you think, but actually the fact that we have such a complicated structure, it will allow us to see that all levels, but a few ones, can be ignored. So this is something very interesting. We have many energy levels, but what I am saying is that out of all those, we can actually forget about most of them and focus only on a couple, or maybe a bit more, but imagine for the sake of simplicity here that it's only a couple. And I will try to convince you of this now with very simple arguments, and later the mathematics will show. But the idea is very simple. So imagine that we have the atom in some ground state. So some atomic state, okay, that it's some kind of, maybe it's the smallest energy eigenstate that you can put the atom in. So we call that G, the ground state. So this is the ground state. I will use this notation from now on. So I will always refer to one state as the ground state, which is the state we start from, let's say. And then we can induce a transition to an excited state. So let's say, roughly speaking, we can take the electron, which is in the lowest possible orbit, and give it a kick to a higher orbit. And we will call that the excited state. Okay. Now, you already know enough quantum physics, or you have heard of enough quantum physics to remember or to realize that the transition of one energy eigenstate to another happens by absorbing a photon. So let me bring this a bit down. Which has energy h bar omega. Okay, so you are sending light. Light is form of these small packets that we call quanta with energy h bar omega, and transitions in the atom happen because the electron, so roughly speaking, the electron absorbs one of these quanta and has energy h bar omega that allows it to make a transition to a higher energy. Okay, so this is the simple picture that, for example, Einstein put forward even before quantum physics was created, like proper quantum physics. However, energy conservation energy conservation tells you that this transition can only occur occurs only if the energy difference between these two levels matches the energy of the quanta. So if you are giving energy h bar omega to the electron, it can jump only to energy levels that have roughly that energy h bar omega difference with respect to the energy that you have, okay? So this is actually very nice, because the other thing that we have already talked about is that each matter transition, or each transition in matter, is unique. So this is what I like to call the spectral fingerprint. Okay, this means that, yes, this structure is very complicated, it has many levels and so on, but if you just focus on two, those two have one specific transition energy, and the only way that you can create that transition, or you can induce that transition, is by sending photons which have energy h bar omega that matches more or less that. Any other level will not feel absolutely anything, because the electrons in those levels just don't have enough energy to do anything. So if they try to absorb this energy h bar omega, they cannot go anywhere. Okay. So this automatically means that we only need to care about the one, so the transition that matches the light's frequency. Oops. Okay, so this is absolutely fantastic. So we start with a Hamiltonian. So what I am saying is, in mathematics terms, is the following. We start with a Hamiltonian that looks rather complicated because it has this representation in its own eigenbasis. Okay, so it has a spectrum that is very complicated. But what I am saying is that if you know the type of light that you are using and it's very monochromatic, or it just have a few frequencies, then you only need to care about a few levels. And in particular, for light that has one specific frequency omega, you only need to care about two levels. So the Hamiltonian that was so complicated, at the end of the day, we can rewrite it just as the combination of two projectors, the ones corresponding to the ground and excited states, okay, that can be connected by that frequency omega. So this form of the Hamiltonian is what is known as the two-level approximation. Okay? So, is there someone not convinced that we can do this? Please, if that's the case, then open your microphone and let's speak about it. I know that you have a lot of trust in me, so I know that you know I am right. But it's not bad if you think that there is something that is sketchy and you want to discuss a bit more. Like, it's nice to counter-argue to understand things better. But anyways, if you don't want to say now, but you have something on the back of your mind saying, no, I don't trust so much this two-level approximation for this and that reason, just feel free to contact me later anytime as well, okay? And I think that this is actually a good point to make a short break, and then we will continue with actually finally some real mathematics of two-level systems and the mathematics of the two-level atom. Okay, so I hope that everyone who was not 100% convinced of the two-level approximation convinced themselves, during this break. But otherwise, I hope that you will get more and more convinced as we go along into the chapter, because we are actually going to calculate things such as what is the probability that light of a given frequency excites an atom and things like this. And we will see that if the energy doesn't match, the atom will not feel anything. But okay, but just allow me for now to do this approximation. So this approximation here, in which the Hamiltonian is approximated just as the mixture of two specific states that play a role in the dynamics, in the quantum dynamics, but nothing else. And then what's interesting is that now we can start developing a mathematical formalism that it's formally equivalent. So the Hilbert space of the atom within the two-level approximation, it becomes equivalent to just the physics of a spin 1/2 particle, because we have a two-dimensional Hilbert space, okay? And there is a lot of mathematical machinery that has been developed for dimension 2 or for spin 1/2 particles, okay? And in particular, you have already seen in quantum mechanics something that are called the Pauli operators, and let me write them down. So we have three Pauli operators, sigma x, sigma y, and sigma z. And what are these? So sigma z is just the excited projector minus the ground projector. Oops. Sigma y, it's I times the matrix element connecting the excited to the ground minus the dagger of that. And finally, we have the sum of the same thing for sigma x. Oops. Okay, and as I say, these three objects, they are called Pauli operators. Okay, now these Pauli operators are super useful because once we describe everything in terms of these operators, they have very nice properties that simplify everything. In particular, I want to discuss here the following properties. So first of all, you know very well that these spin operators or Pauli operators, they are called spin operators as well because they satisfy the angular momentum algebra. So let me write it down and discuss. So this means that the commutator between two Paulis, okay, J and K, it's equal to 2I, another Pauli, sigma L, multiplied by a factor. This is so it's usually called the Levity-Beta symbol or the Levity-Beta tensor. And this is the totally antisymmetric form in with three indices. So this means that if you exchange any of the indices, then you get minus the same number, okay? So I will not explain too much about it because you already know, but essentially this means that the commutator of sigma x, sigma y, it's equal to sigma z, okay? And then permutations of that with the sign of the permutation. So on the other hand, the anti-commutator also has a very simple form for Pauli matrices. So if I ask what is sigma j, sigma k plus sigma k, sigma j, okay, this is actually equal to 2 times the Kronecker delta of j and k and proportional to the identity. So again, do not confuse this I and this I in here with anything related to nuclear spins, please. Nuclear spins are in the past. We are not going to use them anymore. Okay, so this is just the complex unit and this is the identity operator in the space of dimension 2. This automatically means, by the way, that it's also very easy to check from the expression that the square of any Pauli operator is just the identity. Okay. What else? So the next thing that it's also obvious from the definition is that the trace of the Pauli matrices, or the Pauli operators, we will talk about the matrices in a second, it's equal to 0, and that the determinant of any Pauli operator is equal to -1. Okay, so these are the properties that we will use of the Pauli matrices, like all the time, of the Pauli operators, that we will use all the time. And I think they are very natural and that you are already familiar with them, but it's good to just settle them. And then we can go back to them anytime we need. So then now that we have defined these operators, let me rewrite the Hamiltonian in a much more convenient way. So the Hamiltonian, I remind you, is this one in here. So we have the ground state energy times the projector in the ground state, and the excited state energy times the projector in the excited state. But I can always add and subtract identities such that I rewrite the Hamiltonian in this funny form. So the average energy or mid energy times excited plus ground plus, and now the energy difference times excited minus ground. Okay, I didn't do anything. Like if you just expand this expression, you get exactly the expression that we had. But what's important now is that in the Hilbert space of dimension 2 that we are working, this operator here is nothing but the identity operator, okay? So it's just the sum of all the projectors of your space. In this case, excited plus ground. So in other words, this term in here, it's nothing but an energy shift. Or if you want, better, this is equivalent by doing a shift of the energy origin. This is just equivalent to removing this term in here, so that can be done just with a shift of the energy, and keeping only this term in here. But this term in here, we can write it in this very nice form, in which this thing in here is nothing but the Pauli operator sigma set, and then all this prefactor, we just define it, okay, as h bar epsilon over 2, such that epsilon is a frequency instead of an energy. So epsilon equal to E excited minus E ground divided h bar. That's what we will call transition frequency. Okay, and this shift of energy, what we have done, like graphically, if you want to see it, is that we have our two levels, ground and excited here, okay? And what we did is that we moved the origin of the energy to the middle of the transition. So this is very convenient for just all the expressions and mathematics that we are going to do now. So we shift the energy origin, so remember that in the atom, in the hydrogen or the atoms that we have studied, we were putting the energy origin at the moment when the electron and the proton get unbounded, okay? So they get free, if you want to call it that way. And then we jump to the continuous of the spectrum. But now what I am saying is that instead of that, we just move the energy. So our reference for the energy origin, we move it to the center of the transition that we are interested in. and this simplifies the Hamiltonian as you have seen, okay? And of course, this transition has an energy h bar epsilon, okay? So you see that the Pauli operators allow us to do this very simple form of the Hamiltonian. And let me just give you maybe a couple more definitions. So let me see what I want to say. Yes. So just a couple more properties or definitions that are very useful in general for dimension 2 systems, but also specifically for quantum optics. So the first thing is to note, and maybe you know this, but the Pauli operators plus the identity, they actually form a basis in the space of operators. Of course, I mean operators in dimension 2, so which is the Hilbert space that we are working on at the moment. So this, I want to discuss something very interesting about this, because when I say a basis in the space of operators, this might look funny because usually the operators are elements that act on the space of states, right? Which we call Hilbert space. But what's interesting is that you can actually show that the set of operators acting on a Hilbert space, okay, they also form a space that has the structure of a Hilbert space with respect to a very special inner product that is called the trace product, okay? I mentioned something about it in the lecture notes, but for now you don't need to know anything special, but it's just very interesting that the operators themselves also form a structure that has the form of a Hilbert space, yeah? But it's a Hilbert space of operators, not of vectors or kets, okay? But the proof of this is completely trivial in dimension 2, and we are going to do it just in a second. So the idea is as follows. So we are going to do it using representations. So in particular, let me introduce you the representation of the Pauli operators in the basis EG. And it's very important, it's super important that every time you give a representation, you say, how do you order the basis elements and which basis elements do you take? So in particular, when I write this, I mean that the order is this, EG, okay? So then with this order, I don't think I will surprise you if I tell you that sigma x is just this funny two-dimensional, so 2x2 matrix. Sigma y is this one, and sigma z, it's this one, okay? So these are called the Pauli matrices. These are the original matrices that Pauli introduced. And as you see, they come out as the natural representation of these operators that we define. Then, let me consider the following. Let me consider just a linear superposition, or just a linear combination of all these matrices, including the identity. So you see that this will be a 2x2 matrix. The coefficients C are some coefficients that are complex. I will define them in a second. But if I just do this, this linear combination, what I get here is something like this. In the diagonal, I will get C0 plus C3 and C0 minus C3. And then in the anti-diagonal, I will get C1 minus IC2 and C1 plus IC2. Okay? Now, if we just allow these coefficients to be any complex number that you want, it's obvious that we can build any matrix with this. So this can be any matrix. Okay? So now, if this can be any matrix, this means that we can create the representation of any two-dimensional operator with this linear superposition, which means that any operator in dimension 2 can be written as a linear combination of the corresponding identity and Pauli operators. Okay? So is this clear? So just very, very simple proof in this case. And then finally, before I continue with more physical and interesting things, let me just do one definition that is something that you are also familiar with, which are called the raising and lowering operators. And in particular, the lowering operator is nothing but we will call it just sigma. And this is just the operator that connects or creates a transition from the excited state to the ground state, okay? So it's this outer product that brings you from the excited state to the ground state. Now, in terms of the Pauli operators, sometimes I will also call Pauli operator to this one, but in terms of the Pauli operators x, y, z, this is just written in this way, okay? And then the raising operator, as you can imagine, oops, there is only one lowering operator. Sorry, I put operators. And there is one raising operator, which is not independent, it's just the dagger of the previous one, okay? And this is just the outer product between going to the excited state, coming from the ground state. And of course, it's just the dagger of the expression that we have written above. In terms of the XY Pauli matrices. So just a note of warning. So you will see in many papers and in many books that some people call these operators sigma minus and sigma plus, okay? I don't like this notation, so I will not use it throughout the course. And the reason why I don't like it is simply because this looks like these two operators are two different operators, like that have nothing to do with each other, sigma plus and sigma minus. But they are actually the dagger of the other, okay? They are not independent. And moreover, I don't need to complicate the notation. Like I can just define sigma and we are all happy. I don't have to write every time minus or plus or whatever. Okay, just sigma and sigma dagger. But just so you know that this notation is used in many quantum optics books and papers. Maybe you have even used it before in quantum mechanics for angular momentum, the rising and lowering operators. So now the only thing that I want to say about these rising and lowering operators is that they actually have commutation relations that are also very nice to write, which are the following. So if you calculate the commutator between sigma and sigma dagger, you get minus sigma set. And if you calculate the commutator between sigma and sigma set, then you get 2 sigma. And of course, the one of the dagger, you just take the dagger of this expression and you find it. Okay? So this is all I want you to know about raising and lowering operators and about the mathematics of the Pauli operators. And now, if there are no questions, then we can proceed to discuss something very important, which is how do we write atomic states, the most general atomic states. So imagine that I ask you, how can you write in a compact form, in the simplest form, the most general atomic state? So first of all, by most general atomic state, of course, then we mean a mixed state, okay? So it's an operator. Then, because it is an operator, we know that we can write it as a linear combination of just the identity and some linear combination of the Pauli operators. And in particular, let me write this combination in this way. Where we usually define a vector operator which contains the three Pauli operators. Okay. And then these coefficients here, B0 and this vector B, which will have components B1, B2, and B3, are just the coefficients of the linear combination that correspond to any atomic state that I want to write. So this we know just from the fact that the Pauli operators and the identity form a basis for any other operator in this space. However, because the states or density operators must satisfy some very specific properties, these coefficients B in here will have certain restrictions. And this is what I want to discuss now. First of all, because rho needs to be self-adjoint, this automatically implies that the BJs are actually real. Okay, they are not complex coefficients, they are real coefficients. Second, because the trace, as you know very well from the exercises, because the trace of the state needs to be equal to 1 so that we can give it a probabilistic interpretation and so on, then this automatically means that B0 has to be equal to 1. And why is this? Because if we take the trace of rho, this is equal to the trace of the identity, which is 2, and the trace of the Pauli operators, but we have seen that the Pauli operators are traceless, right? The trace of of sigma is equal to 0 for every sigma. Therefore, this expression, the trace of rho, is just equal to B0, because the trace of the identity is equal to 2 divided by 2, 1. Okay? And then finally, the eigenvalues. So remember that rho needs to be positive, right? So let me maybe write it here. So we use this notation in which we were saying that an operator we write that is larger or equal to 0 when the eigenvalues of the operator are larger or equal than 0. And this is called that the operator is a positive semi-definite. And this is one of the properties of density operators. And then because of this, so because of this property, which essentially means that the eigenvalues need to be positive, as I was saying, but the eigenvalues of this operator, which is a 2x2 matrix, if you want this 2x2 matrix, but changing C0 by 1 and the C's by what we have been calling B now, are very simple. The eigenvalues of this are completely trivial. It's a 2x2 matrix, and you can check that the eigenvalues are just 1 plus minus absolute value of B. Okay, so this automatically means that the B's that we can write for physical quantum states are not any B, but they must be upper bounded by 1. Okay? So, in other words, so let me summarize. The most general quantum mechanical state of an atom, including mixed states and everything you can think of, can be written as the identity plus a real vector times the Pauli matrices, or the Pauli operators, where the B must necessarily have magnitude, a modulus, smaller or equal than 1. Okay? So look how nice this is. So in general, operators in a Hilbert space, okay, might be complicated and so on. But we have been able to map the quantum mechanical state of an atom to just a vector in 3 dimensions, a real vector in 3 dimensions. And this is actually very useful because also these components of B have a very, very nice interpretation, and they will allow us to make a very nice representation of states, quantum mechanical states, in some space, 3-dimensional space that we call the Bloch space. And let me show you this. So in particular, let me start with the interpretation of the BJs, or the B operator, sorry, the B vector. So what happens if I ask you what is the expectation value of one Pauli operator sigma j? So this is equal to the trace, just by definition of expectation value with a mixed state. This is the trace of rho times the operator. But rho has this form, okay? This form in here. And therefore, this will be equal to just 1/2 of the trace of the operator itself, because the first part of rho is just the identity, plus, and now we have the sum over k of bk times the Pauli operator sigma k, but then now we have the trace with the Pauli operator, oh, sorry, this is sigma j. And now we have here sigma k. So I hope that this is obvious to you, but it just comes from this expression. Just multiply sigma, rho by sigma j on this side, and you will get exactly sigma j in here. And here you get a sum of the components of B times the components of sigma times the sigma j. So it's exactly this expression here. Now, from the properties of the Pauli matrices, this combination, or this multiplication of sigma k, sigma j, okay, this is equal to delta kj times identity plus I times the sum in L of this antisymmetric symbol kjl sigma L, okay? This you can just see very easily from these properties that we wrote for the Pauli matrices, or the Pauli operators, in which we say that the commutator is equal to this and the anti-commutator is equal to this. So if we just add them or subtract them, in this case, this minus this, we get exactly this expression. But then now everything is very simple, because we know that the trace of the Pauli operators is 0, and now the trace of the product, it will be equal to the trace of the identity, which is 2. So this is 2 delta kj, plus the trace of the Paulis, which is 0, multiplied by something, so it's 0. So then when you put everything together, this is equal to what? Bj. This is awesome. Look, the expectation values of the basis operators, sigma j, are exactly the coefficients B that we write for the parametrization of the state. So if I give you the state in this form, you automatically know that the linear coefficients, so the coefficients of the linear combination of the sigmas, are exactly the expectation values of the Pauli operators for that state. Okay? This is really nice because it allows us to make a representation of states of atoms, of atomic states, in something that we call the Bloch space. And let me see if I can plot it beautifully. I hope I can. I will try my best. And this space is just the following, it's just a space in which what we do is that we have 3 dimensions, and on each dimension we write the expectation value of a Pauli operator. Okay, so this space in which we specify by 1 point what is the expectation value of the Pauli operators, we call it Bloch space, and states can be represented as points in this space. In particular, this B, it's exactly that that vector, and it gives you what is the state. And in particular, this state will have some components, okay, Bx, By, and Bz. So let me do Bz with a bit more care. Okay, and then when I specify one state like this, then you know exactly what I mean. So we have a 3-dimensional representation of a 2-dimensional Hilbert space or atomic states. So this is a very nice thing, because this is one of the few Hilbert spaces where we can actually represent, still we can represent the states in a very nice way, even mixed states. Okay. Then what I want to say about this, just a few more things. Oh, by the way, we will call B, since this is a coordinate vector in Bloch space, we will call it Bloch vector. Okay? And then now what I want to discuss is the following. So imagine if I ask you what is a maximally mixed state of the atoms. So what is the B corresponding to the maximally mixed state? Anyone can tell me? So think about it. I give you a hint, it's not B infinity, so is it Jan?
B equals 0.
Exactly. So when B is equal to 0, you see, just by the parametrization of the state, that you get the identity divided by 2, which is exactly the maximally mixed state in dimension 2. So you have seen that B equals 0 is the maximally mixed state. So this is very nice. Now, let me make a bit more space. I think I will need it. Now, the next thing I want to discuss, it's, as you can imagine, the opposite limit. Imagine that I ask you about pure states. So now pure states are not only one state, it's a family of states. There are infinitely many pure states. But all of them must satisfy something very special, because we have seen that the eigenvalues of the density operator are 1 plus minus absolute value of B, right? So magnitude of B. But if I tell you that rho is pure, it means that it has only one projector contributing to the mixture, which means that it has one eigenvalue that is equal to 1, and all the rest are equal to 0. That's the definition of a pure state. Mathematically, we say that rho is a rank 1 projector, okay? But in any case, what's obvious is that in dimension 2, whenever the eigenvalues are 1 and 0, then rho is pure. And when are the eigenvalues 1 and 0? When b is equal to 1. So the magnitude of b is equal to 1. So in other words, pure states are states for which b are equal to 1. So if I give you a b whose absolute value or magnitude is equal to 1, then you know that these states are pure states, or this state is a pure state. And for pure states, there is a very nice parametrization, because when I say that in this space, we set the magnitude of b equal to 1, this means that this vector has modulus 1, right? So this means that I can do a parametrization of this vector in spherical coordinates, and in particular in these coordinates here. So cos phi sine theta, sine phi sine theta, cos theta, where theta I will take it between 0 and pi, and phi I will take it between 0 and 2 pi. Okay? So these are called spherical coordinates, as you know very well. And why I write this, just because it's very simple to check that with this parametrization, pure states are written in this very simple form. So as cosine of theta over 2 ground, sorry, excited. This depends on conventions. So I chose this convention here. And then e to the I phi, and sine of theta over 2 ground state. So look, this is really, really nice, because if you know that the magnitude of b is equal to 1, then this angle here gives you the relative phase between the excited and the ground state in the quantum superposition. And this angle here gives you how much weight do you have in the excited and the ground state, okay? The cosine of theta over 2 and the sine of theta over 2. Moreover, the condition b equal 1, or absolute value of b equal 1, defines something that we call the Bloch sphere. And it's a very, very special object, because all, so essentially all pure states lie in this sphere. And I will show you some very pretty pictures later with this of states in this Bloch sphere and trajectories in this Bloch sphere. But for now, it's just a funny thing that pure states lie, all of them, in a sphere in the Bloch space. And let me try to make the sphere as well. So I will try my best to do it properly. So let me see. Okay, I need first this, and then now I will do in here something like this. Okay, so essentially all pure states lie in this Bloch sphere. And if you transform pure states into pure states, you will always make trajectories along this sphere. Okay, then let me just tell you or give you one more definition that will be important before starting with more physical dynamics stuff, which it's something that we call populations. And the populations are just something very simple. It's just a very simple quantity in which we just ask what are the probabilities of being in the ground state or the excited state. So it's exactly these objects here. Okay, so we will call population or ground state population or excited state population to the probability of being in the excited and the ground state. And in terms of the B, so in terms of this Bloch vector, this is just given by 1 plus the third component of the vector over 2 and 1 minus the third component of the vector over 2. You can check it yourself. So these are objects that are very important in quantum optics, like talking about populations of how much of the electron is in one state or the other, okay? And we give it a special name, populations. Okay, so I hope that this is clear. This is everything I want to tell you about how we parameterize states in quantum optics, so atomic states in quantum optics. And what I will do now is we are going to see how the evolution of atomic states with this parametrization in terms of the Bloch vector allows for a very simple way of deriving the evolution, not with the von Neumann equation or with the Schrödinger equation, but with an even simpler equation that we call the Bloch equations, okay? So imagine, so for this, imagine that I tell you that I want to do unsupervised evolution, or our atoms undergo unsupervised evolution, which means that we don't do anything on them, and then they just evolve according to some Hamiltonian, okay? That maybe we have engineered in the lab or something like that. So the first interesting thing that we can discuss is what is the most general Hamiltonian. So in dimension 2, so in a Hilbert space of dimension 2, again, using the fact that the identity and the Pauli operators are a basis for any operator, then we can actually write down the most general Hamiltonian acting on our atoms. We can write it in this simple form. So I will use a normalization on h bar over 2, and then some parameter, so alpha, that might even depend on time, okay? And then the Pauli vector, where these coefficients, alpha, this vector, these are real functions of time. So these are functions that take from the reals, so from the time t, into 3D, real 3D. And this is obvious because the Hamiltonian needs to be self-adjoint. And the Hamiltonian is only self-adjoint if alpha is real, okay? So this is the absolutely most general Hamiltonian that you can get in dimension 2. So there is nothing in dimension 2 that you cannot write in this way. No Hamiltonian that you cannot write in this way. So in particular, the most general Hamiltonian has time-dependent coefficients, okay? But of course, in many situations, you only need time-independent coefficients. Okay, then now let's talk about evolution. So the evolution, so typically, like for example, you showed in the exercises, the evolution is given by saying what is the state at some given time. So what is the density operator at some given time. But with our parametrization of states, so once you know that any rho can be written in this way, then if I put time dependence on rho, that's equivalent to putting time dependence on the parameters B. So in other words, in Bloch space, time evolution means simply that the coordinate vector B is moving in time, dt. So now the question is, how do we find the dynamical equations of B? So the dynamical equations that tells us how the time derivative of B behaves in time, okay? So we know that B, okay, is nothing but the expectation value of the Pauli operators. So we can simply use the Heisenberg equations of motion of the Pauli operators and then take the expectation value. That's a very simple way of proceeding, and let me write it down explicitly. So we write down the Heisenberg equations of the Pauli operators, and these look like this. So the Pauli matrix, the Pauli operator J, the time derivative of that, according to the Heisenberg equation, is just the commutator between the operator and the Hamiltonian, and divided by IH bar. But we know what is the form of the Hamiltonian, so we have it here. This automatically means that we have minus I over 2, then sum over k, alpha k that depends on time, and then the commutator between sigma j and sigma k. But we know what is the commutator between sigma j and sigma k. And if you use it, you will just get this very nice expression. So you have the totally antisymmetric symbol, and then you have alpha k of t and sigma L. So these are the Heisenberg equations of the Pauli operators. And if we now take the expectation value of this expression, we get, remember, we are in the Heisenberg picture, so states are time independent. So when we take the expectation value, we can put the state inside this time derivative, and then we get here the derivative of the expectation value. And this is just B dot. And this will be equal to the sum in K and L of the antisymmetric symbol, alpha K times B L. Now, this expression is very nice because this is a linear system of equations, and in particular, let me rewrite it in an even more compact form in terms of matrices. So the vector B evolves in time according to a linear system defined by a matrix B that looks like this. So let's see if I left enough space. Almost. And let me be clean, since we can be clean. So we get this expression here. So these are called the Bloch equations of the atom. Okay, and look, this is really, really nice because we have taken the Schrödinger equation or the von Neumann equation or the Heisenberg equation, so the quantum mechanical equations of motion, and we have mapped them to a very simple linear system for 3 variables that have a very nice interpretation in the Bloch space. And this means that essentially we will take the starting point of B at time 0, and then we will be moving around with some trajectories, and we will see some of these trajectories now, according to this very simple linear system of 3 equations. Now, since this is a system of 3 equations, no matter which Hamiltonian I give you, so no matter which functions of alpha of t I give you, you can always solve this linear system in a very simple way, many times analytically, but in the worst case, just numerically. You have 3 equations. We have computers in the 21st century, sorry, which means that we know how to encode this in Mathematica or MATLAB or Python or whatever you like. And then you can just simulate the dynamics of any atomic system within the 2-level approximation. And of course, if you want to add more levels, things get a little bit more complicated, but you can imagine that not infinitely many, infinitely more complicated. So then this is a very nice way of representing atomic states that allows for a very efficient numerical computation in the worst case. But we are even going to see now some analytics for very special types of evolution. But before I show you those types of evolution, let me do a couple of remarks. So the first remark is that it's very simple. So it's written in the note, but I invite you to do it yourself. That the time derivative of b squared is equal to 0. So this means that when you do a unitary transformation or you do Hamiltonian evolution on your state, the evolution happens, so these trajectories in Bloch space happen in a specific sphere that has radius b0. Okay? So this is a sphere, so b equal, so the absolute value of b or the magnitude of b equal to the starting point that defines a sphere in the Bloch space, and then everything happens within that sphere. But this is actually not surprising because we already know that if you remember, the entropy that characterizes how mixed our state is depends only on the eigenvalues of the density operator, right? And we also know that unitary transformations do not change the entropy, okay? The entropy is unchanged by unitary transformations or by Hamiltonian evolution, which it also makes a lot of sense from the informational point of view of mixed states that we talked about. Therefore, what happens is that unitary transformations cannot change the entropy. The entropy depends only on the eigenvalues, which in turn depend only on B, on the magnitude of B, and therefore the magnitude of B cannot change under unitary transformations because that would change the entropy, okay? So in other words, if you fix the entropy of your system, of your atom, then Hamiltonian evolution will occur within the sphere that corresponds to that given entropy. So different spheres in this Bloch space define different entropies for your states. Okay?
Excuse me.
Yes.
I'm a little confused. Why can we use Heisenberg equation to derive the evolution of B? Because
so it's very simple for the following reason. So I know it looks funny because B, it's a parameter in the state, right?
Yes.
So then naturally you would think that you use the Schrödinger equation or the von Neumann equation to find the evolution of B. But at the same time, we have seen that B is nothing but the expectation value of an operator, right? And the expectation value of the operator, you can find the evolution in the Heisenberg or the Schrödinger picture. It's exactly the same. So the expectation value of the operator does not depend on the picture, okay? So in particular, if I find the evolution of the operator sigma, okay, which of course, because it is an operator, it's given in the Heisenberg picture by the Heisenberg equation. And then I take the expectation value with the initial state, so the state at time 0, or the Heisenberg picture state, which doesn't depend on time, then I get B. I get B at any given time.
Okay.
So is that clear? So just look, it's very simple. So just forget about B for 1 second. Imagine that I ask you, calculate the evolution of your atomic system, and you choose the Heisenberg picture. Why not? Okay. Then you find the evolution equation of your operators. Once you have the evolution equation of your operators, now I tell you, evaluate the expectation value of those operators, and that's equal to B. Okay?
Okay.
So this is just the simplest or the fastest way of finding that. I also encourage you to find it in the Schrödinger picture, because you can do it also in the Schrödinger picture. You can ask, what is the time derivative of rho? Okay. You write the von Neumann equation. That's the commutator between the Hamiltonian and rho. And now you write the state rho. You write it in this way and use the properties of rho. Okay. And you will find exactly the same equation. You will find this equation here. Okay, maybe you can try it as an exercise. So same calculation in the Schrödinger picture. And if it's not clear how to proceed, then I can show you, I can send it to you all. Okay?
Okay, thank you.
Let's do something. No matter what, I will send it to you. So I give you a few days, and please tell me if you manage to find it. Okay?
Yeah.
Okay. So I hope that's clear. And then the other remark I want to make is just a more convenient representation sometimes. So let me just write more convenient representation of the Hamiltonian, which is in terms not of the Pauli matrices or Pauli operators X and Y, but in terms of raising and lowering operators. So in terms of raising and lowering operators, the Hamiltonian can be written in this way. So we don't touch the sigma set part, but then the XY part, we write it in this way. In terms of raising and lowering operators, where, of course, this alpha t, it has a relation with the previous X and Y components of alpha, that is this one here. Okay? Then in terms of this complex representation or raising and lowering operators, we can define a B variable, which is just the expectation value of sigma, and it will be exactly equal to bx minus iby over 2. So this variable here, instead of bx and by, this complex variable, okay, this is similar to what we did for the harmonic oscillator, that instead of position and momentum, we use a complex variable related to the annihilation operator. So here is something similar. So in terms of this complex variable, actually the Bloch equations look very simple and, or at least very nice. And it's exactly this expression that I'm going to give you. So we have only two equations because one of them is complex, the one of B, and they look like this. Okay, so these equations here are known as the complex Bloch equations. but we will usually just call them Bloch equations. It's just another form of them. And it's very nice because, well, you see that you have only two variables, B and B set. One of them is complex. And then you have a linear equation just with two terms, and then another linear equation just with one term and the complex conjugate. This is always the complex conjugate because B is real, B set is real, okay? So then this form is very useful, and it's going to be very useful for the next derivations. Okay, so if everything is here clear, now let me start talking about some specific Hamiltonians that are very important in quantum optics. And the first one is just the Hamiltonian that we can call do nothing on the atom. So do nothing on the atom, so that statement, it simply means that we just have our atom and it's evolving according to the Hamiltonian of the atom, the atomic Hamiltonian. And the atomic Hamiltonian, we already wrote it in this way. Okay. So the question we are asking is, we prepare a superposition of ground and excited state, or in general, a mixed state of ground and excited state. And we just let the system evolve in time according to its own Hamiltonian. What will we find? So is it very trivial, a bit complicated? Well, this is equivalent, or this Hamiltonian has the form, this form in here that we have written for a completely general Hamiltonian. But now alpha is going to be equal to 0 and 0 in the components x and y, and epsilon in the component z. Okay, so just alpha is equal to this. Then the Bloch equations in the complex form are given by just this equation here. Okay, and these equations here have the trivial solution of B at time t, it's equal to B at time 0 in a phase, and B set at time 0, at time t, it's equal to B set at time 0. Of course, we were expecting already the B set equal or independent of time. Why? Because the Hamiltonian is sigma set, and it commutes with sigma set, which is the expectation value that defines B set. Okay. So in other words, if you prepare a state that has some population in the excited state and some population in the ground state, okay, those probabilities of being in the ground state and in the excited state will not change in time. And this you also saw in the first exercise that you did regarding just basic quantum mechanics, that the probability of being in the eigenstates of the Hamiltonian doesn't change in time, obviously. Okay, so in terms of the original Bloch vector variables, so we can visualize them in Bloch space, this means that B of t is just a rotation in the x-plane. So let me just write it down. Sorry, in the z plane. Sorry, in the z, around the z axis. That looks like this. Okay. So if you rewrite this expression, this complex expression in terms of x and y components, then you will get just this simple rotation. And in particular, this is just a harmonic right-handed rotation around the z-axis. And this is sometimes something that you have heard that it's called spin procession. Okay. So right-handed, by right-handed I mean that you can be right-handed or left-handed, and then you follow the thumb rule. Okay. So you put the axis in your thumb, and then the rotation happens in the direction of your fingers. Okay. So in particular, let me show you which trajectory this describes in the Bloch space. And so for this, let me bring in this picture that I prepared. So I hope you can see it well. So this is Bloch space. So we have sigma z-axis, sigma x-axis, and sigma y-axis, expectation values. Now, imagine that you start from a B, okay? Doesn't matter which B. So you start from some B that has some radius, and then it defines a sphere, okay? Then the evolution will just happen by a rotation in this way, okay, right-handed, around the z-axis. So you start from this point, and then you describe a circle in the sphere. It's a circle embedded in the sphere, okay, around the z-axis. So this is the simplest type of evolution that you will find, and this is telling you that atoms always have this. So you will always have this kind of effect in which you start from any state, but as the time progresses in time, you will always be doing some kind of spin precession, and you have to be careful with that. You have to take that into account. In particular, what this means is that the relative phase between excited and ground state for a pure state, for example, it changes in time. But of course, the probability of being in the excited or the ground state remains fixed because you are doing the rotation around the z-axis. So you are always at constant z. Okay? So I hope that this is very clear. So if this is clear, then we can proceed to more complicated types of evolution. And in particular, I want to discuss the most important type of atomic evolution in quantum optics, which is known as Rabi oscillations or Rabi evolution. Okay, and this will also allow us to introduce an approximation that is super important in quantum optics, and you will be doing throughout your life. If you work in quantum optics, you will be using it all the time in many different types of systems, okay, which is called the rotating wave approximation. And these 2 points are very, very special and very important, so we will give them a bit of time. So I don't think that we will be able to finish it today. We have only 15 minutes left. But at least I will introduce the rotating wave approximation. Okay, so let me start by giving you the Hamiltonian that we are going to analyze. And the Hamiltonian is called the semi-classical Rabi Hamiltonian. Okay, so the semi-classical Rabi Hamiltonian, we call it semi-classical because, as we will see in the next chapter, I will not show you now, but in the next chapter, when we study the interaction between light and matter, okay, we will see that this Hamiltonian describes the interaction between classical light. If you want classical monochromatic light, so maybe I should add it here. And the atom. Okay, so we have interaction between a classical monochromatic beam of light So how do we do this? Maybe we will also see it in this course, or you will see it in future courses of quantum optics, but we do it with the laser. So the laser creates such a monochromatic beam of light, and for large intensities, this is a coherent state, and it's therefore a classical state, classical monochromatic light. And when you shine this kind of laser light into an atom, what you get is a Hamiltonian that looks like this. And as I say, we will prove this in the next chapter, but for now, just take it as one interesting Hamiltonian that we will analyze and we will justify in the next chapter. Okay? So this Hamiltonian it's very interesting. It has the free evolution of the atom, so that's always there. You cannot remove it. It's part of the atom. But then on top of that, you force the atom with some time-dependent term, okay? Some time-dependent Hamiltonian that goes not in the direction of sigma set, so the natural direction of the atom, but in an orthogonal direction that we have taken as sigma x, okay? It could be any direction that it's orthogonal to sigma set. That's controlled in a quantum optics experiment. That's controlled by the relative phase between the quantization axis of the atom and the beam of light, okay? The phase of the beam of light. So in any case, we have a time-dependent perturbation, if you want, to the Hamiltonian of the atom, and we need to study how this makes the atom evolve, and we are going to find a lot of interesting things about this, even though it looks like a very simple Hamiltonian. So in particular, this Hamiltonian, in the language that we were using in here of writing the Hamiltonian as a linear combination of Pauli matrices or Pauli operators, this is just equal, so it's just defined or given by an alpha, so the linear combination that has alpha x equal to omega cosine of omega t, 0, and then epsilon, okay? Perhaps let me say just a couple more things about the relation between omega, these parameters, capital omega and small omega, and the light field. So we will see in the next chapter that this omega, obviously from the notation, is just the frequency of the monochromatic beam. That's the frequency that I was also using at the beginning of the chapter to convince you of this two-level approximation and so on. So it's the frequency of the photons that the atoms are absorbing. And this omega here, that's a parameter that's related to the intensity or the magnitude of the light field that you are shining on the atom, and also on the dipole moment of the atom. So it's the multiplication of these two, okay? So in particular, this is a parameter, omega, that can be controlled with changing the intensity of the light beam. However, there are a couple of interesting things. So, so let's talk first about the expectations that we have. So the expectation is that omega, when it is far from epsilon, okay, then nothing happens. Or if you want more than nothing happens, this is equivalent to free evolution. Okay? This is the first expectation. And this is where we are going to get to prove, okay, to prove mathematically that if the frequency of the radiation is not close to the transition between the ground and the excited state, and we will define what close exactly means, okay? Then it's like we are doing nothing. It's like the atom doesn't see the external light field. On the other hand, we will do one assumption, but that, as I said, we will show in the next chapter that it's very natural, which is that this omega, okay? So this coupling between the light and the atom, it's actually much smaller than the frequency of light, okay? The frequency of light is approximately 10 to 15 hertz, okay, in optics. This is quite a large frequency, okay? And in order to get to amplitudes omega or to interactions omega that are on the order of 10 to the 15 hertz, you would need intensities of your light beam that basically destroy your sample already. So experiments basically cannot occur for a single atom interacting with a light field, cannot occur in a limit in which omega is on the order of the frequency. That's too much intensity, it's too much energy that you are shining on your material, okay? However, it's very interesting that in recent times, there have been other systems in which you can engineer this kind of Hamiltonians, okay? So exactly the same type of Hamiltonian. We say that you can do quantum optics with it, but these are not atomic systems, but engineered systems that also have a non-uniform spectrum, but the frequencies that you can work with are, let's say, much smaller than optical frequencies, okay? And the coupling is not between a light field and an atom, is between your artificial structure that you have created in the lab and something else that could be light as well, but it can be other types of electromagnetic radiation, like in a circuit or something like that. Or it could even be that you are not using light at all, that you are using mechanical oscillations to drive that system and so on. And therefore, this parameter omega can get to the order of the frequency, okay? So therefore, what we are going to see here is very specific for optics. And if you are interested on going beyond what you can do in optics or quantum optics, and in particular, you want to reach regimes in which the modulation amplitude of the Hamiltonian is on the order of the frequency, then you can do it in other systems that we can study or that you can study in some project, okay? So essentially, this is the Hamiltonian that we are going to study. And since I only have 5 minutes left, I don't want to continue, because what we will do now is we will write down the Bloch equations associated to this Hamiltonian, and we will solve them under an approximation called rotating wave approximation that we will justify properly, okay? So this will be the last thing of this chapter. So as you see, this chapter is a short chapter compared to the previous one that took us already several weeks. But then in the next chapter, we will use a lot of machinery from this chapter and combine with the previous one to do interaction between light and matter, which is something super, super interesting.